Delaware Tech, Chemistry 100, Chemistry 110, Unit 3 continued, Trends in the Periodic Table. There are multiple trends of different properties of elements that are apparent in the periodic table. One side of the periodic table tends to have higher values than another side or another corner, and these are referred to as trends. There are 3 or 4 trends we're going to talk about in this course. 2 of them will be discussed here. The first one is a trend in atomic radius, and this is really a measurement of the size of an atom. We can think of the atom as roughly a sphere. Let's draw that. So just draw a ball here. We have the nucleus in the center, a tiny little dot, and the distance from the nucleus to the outermost electrons, that would be the radius of the sphere or the radius of the atom, and we call that the atomic radius. And this is influenced by 2 factors. One of them is very obvious, and the other one is not so obvious. The first factor is the energy level. That is, as you look down the periodic table, as you go down the periodic table, you've got elements at the top of the periodic table. I'm just drawing it as a simple rectangle. So the elements at the top here are small, and pardon my horrible handwriting, and the elements down here are large, because each row that you have in the periodic table, you're adding huge volumes of space with new energy level orbitals that take up much, much larger volumes. And therefore, you get much larger atoms that are down at the bottom with higher atomic numbers than the ones at the top with lower atomic numbers. And that's pretty obvious right off the bat. The higher the period, in other words, further down the periodic table, the larger the size. So as you go down a group, meaning higher period number, you get a larger and larger atom. The second one is not so obvious, and this is a factor that influences radius as well as the other term that we're going to talk about in terms of trends. This is the charge that's resulting from the nucleus, and we actually have a name for this. We call it the effective nuclear charge or the effective nuclear force. And what this means is that as you go from left to right on the periodic table, so across a period, you are looking at atoms that have more and more protons because their atomic number is increasing. Well, it turns out as you add more protons across the periodic table from left to right, you increase the positive charge of the nucleus. Well, that makes sense because you're adding more protons. And what that does is every time you add a new proton, as you go from left to right, you pull the electrons in that are there a little bit closer. And you can envision this, that the higher the group number, in other words, the group numbers are numbered from 1 to 18, the ones over on the right are actually smaller. And we'll talk a little bit more about that when we look at drawings of the atoms themselves. So in this case, this is counterintuitive that the smaller elements are on the right side of the periodic table. They're not, as you go across to increasing atomic numbers, you would think, oh, that's getting bigger. But no, in fact, it gets smaller as you go across. So let's look at this in terms of the two different factors. As we go down, we add a new energy level. So if you look at the first group, group 1, hydrogen, lithium, sodium, that's Na, potassium, that's K, rubidium, cesium, francium, down the row, as you go down the columns, in other words, down the group, you add huge volumes of space every time you add a new energy level to that atom. Remember, the last orbital for this one was a 1s, this was a 2s, this was a 3s, this was a 4s, and this was a 5s, and these things add huge volumes to the previous orbitals that were already there. And the fact is, these can add a lot of volume, and so going from hydrogen to rubidium is actually 100-fold or more increase in the overall volume of these atoms. So these are big effects. Now, going across the periodic table from left to right, this is the one that's not so obvious. And that is because if you start with sodium, remember sodium has an atomic number of 11. So that means there are 11 protons in here. And that means there are 12 here, and 13, etc. 14, 15, 16, 17, all the way to 18 protons by the time you get to argon. Well, it turns out that, yes, this has a 3s orbital for the last electrons of these two, and the last electrons for these 6 are in a 3p, the 3p set of orbitals. But the fact is, if you look at the size of the 3s orbital, and then you look at the individual sizes of the 3p, remember the 3p are 3 different dumbbells, they actually fit in the same volumes of space, so you're not really adding any volume by going from 3s to 3p. So that doesn't increase the volume. So the question is, why is it being decreased? Well, it's decreased because this has 11 positive charges in the middle, 12, 13, all the way up to 18 positive charges. And these positive charges are drawing the electrons in tighter and tighter as you add more protons. So you end up getting smaller as you go from left to right on the periodic table. The large ones are on the left, and the smaller ones, are over here. And that's the other trend, and that is due to the effective nuclear charge, sometimes called the effective nuclear force. And I'm going to erase these notes here. And so it's the opposite of what you expect for left to right. The top to bottom makes a lot of sense. Left to right is a little more confusing to a lot of students. So it's effective nuclear charge. It's pulling the outermost electrons in towards the protons in the middle. They're being attracted. Opposites attract. So what that looks like, if we plotted each of the atoms' size in terms of the radius versus their atomic number, we start with hydrogen, it's small, and helium is even smaller. So helium is actually the smallest of all the atoms on the periodic table, the upper right-hand corner of the periodic table. And then we go from helium to lithium, the next row, and suddenly there's a big jump. We jump up. But then it trickles down because of the effective nuclear force within the row until you get to neon, so it's a bit smaller, but not as small as hydrogen or helium. And then once you're here after neon, well, the next atom is sodium, Na, in the next row, and boom, you get a huge jump up to sodium, and then it trickles down due to the effective nuclear charge or effective nuclear force. And then after argon, you go to the next row, you hit potassium, huge jump up in size, but then it trickles down because of the effective nuclear force again. And in this case, you see this little hump here. Well, the little hump is because that's where the 10 transition metals are located. Roughly 10 of these dots, almost about 8 or 10 of these are transition metals. And that is because transition metals are just very complicated as far as where the electrons are. It's much more complicated than just saying which orbitals they are. There's a whole field that studies this called crystal field theory, and that would require weeks of study to really understand. I will not make you responsible for that. So I will always restrict myself to the group A elements when I'm asking you to compare sizes of something or any of the other trends, because the transition metals are far too complex. So if you go to the next row, again, you get this big jump between krypton and rubidium, and then it trickles down to xenon. So this happens over and over again, and you get this unusual zigzag pattern. And if you looked at the relative size of each of the atoms on a partial periodic table here, you see there are huge jumps whenever you go down. Big increases in size. Maybe not so much on the right side of the periodic table because you're starting small to begin with. And the smallest atoms are up here, and the largest atoms are down here. Here's large, here's small. So we have this trend where the bigger ones are down there because the increase is going this way and the increase is going this way, and that adds up to an overall diagonal trend in this direction. So the second trend I wanted to discuss was a trend in a property called ionization energy, also known as ionization potential. So these are abbreviated as IE or IP. They mean exactly the same thing. And this is the amount of energy required to remove the outermost electron, typically from a gaseous atom. And this is the energy. It's referred to as the first ionization energy if you're removing just one electron. And so when you do this, when you remove one electron, you're going to end up with a positively charged ion, a +1 charged ion. And atoms that are okay with doing this tend to have a low ionization energy because if it's easy to remove the electron, that's low amount of energy to kick it out. And if it's very difficult to remove an electron, well, that's going to be very hard to kick out. So this is especially true for the elements on the left side of the periodic table. Let's keep hydrogen aside for a second, but look at the alkali metals, the ones on the left side of the periodic table in group 1. So we're talking about lithium, sodium, Na, potassium, that's K, rubidium, cesium, and francium. These metals are fairly happy, and I use the word happy, obviously, in the anthropomorphic sense here, but they are stable stable in losing a single electron. And the reason why is when they lose a single electron, it makes their electron configurations look exactly like the noble gas that is right before them on the periodic table. Remember, lithium was 1s2, 2s1, but if you remove that 1, all you're left with is 1s2, and that's the electron configuration of helium, extremely stable gas. So they all want to lose one electron to be like a noble gas. Now, the second and third ionization energies, in other words, the energy to kick out that second electron, the second outermost electron, and the third most, the outermost electron, those are always harder. It's always harder to remove the second electron than the first. It's always harder to remove the third one than the second. And that's because each time you remove one, you're making the atom more and more positively charged, so it's a little more difficult. Now, the trends in the ionization energy are due to a couple factors, just like they were due to a couple factors with the radius. Within a group, so we're looking down a column on the periodic table, the ionization energy decreases. In other words, it gets much, much easier to remove an electron as you go down the periodic table. And that is because the electron, the outermost electron, is in a much bigger atom, remember that from the size, and therefore it is much, much further away from the center of the atom, the nucleus. So if we look at this in terms of a very simple drawing of our atoms, we have the nucleus in the center, and here's the outermost electron here. And we have a big atom, and maybe there's the nucleus, and we have the outermost electron way out here. So first of all, there's a much bigger distance. So that makes it easier. It's always easier to pull something away from a nucleus that's very far away than pulling that electron away from something where the nucleus is right up against the electron. But in addition, remember, this atom has many electrons in it, especially larger atoms, and they get in the way. And they kind of block the feel of this giant positive charge in the center, and we call this shielding. So the larger the atom, the more shielding, the more electrons that are between the center, the nucleus, and the outermost electron. They're kind of blocking the effect, and we call that shielding. So it makes it much easier to remove electrons that are further away from the center, from the nucleus, in other words, a larger atom. The other effect is within a period. So now again, we're looking from left to right, and just like with the atomic radius, we have this effect that's partly due to the effective nuclear charge. In this case, it makes the ionization energy increase as you go from left to right. In other words, the outermost electrons in the atoms in the same period, they have the same energy roughly, but they experience roughly the same amount of shielding because there's not that much difference in size, There are not that many electrons that are lower than them, and they're roughly the same number within the same row. But the effective nuclear charge is pulling those electrons in tighter, and the atoms are also a little smaller on the right side of the periodic table. So you end up having this effect where if we look at atoms on the left, and here's an electron, the outermost electron here, and we look at atoms on the right, which are going to be a little smaller, that'll make it harder to remove. So this will be harder to remove, and therefore it'll be it'll have a higher ionization energy. But the electrons that are in the center, it's the same core within a row. You'll have the same number of center electrons in here that are kind of shielding as before. The outermost electrons, what we call the valence electrons, and we'll talk about those in the next unit, those numbers change within a row, but the innermost electrons, those aren't changing much, so the shielding isn't going to be different. So really, you have this effective nuclear charge pulling them in tighter when you have more positive charge on the right side of the periodic table. So what does this mean in terms of trend? Well, you have this weird pattern here. If you plot each of the atoms in terms of their atomic number on the x-axis and their ionization energy, but you might say this doesn't make any sense until I put some lines through. Each line represents one row on the periodic table. So this is the first row, the first period, the second period, the third period, and the fourth period. The fourth period is where you start getting transition metals that complicate things. So we're not going to worry about those right now. But you see in each row, the left side of the row, hydrogen, has a lower ionization energy than the right side. Noble gases like helium, neon, argon, krypton, they're hard to remove that outermost electron. They don't want to lose an electron. They have a full row filled with electrons, and in terms of electron configurations that we talked about, the most stable configurations are when an entire row is filled with electrons. And these noble gases have full electron configurations in their outermost row, and actually in all of their rows. Whereas the ones down here, and we'll include rubidium, these have an extra electron that they are happy to lose to be just like the noble gases. Lithium, if it loses one, will be just like helium. So lithium and sodium and potassium and rubidium, and to a lesser extent hydrogen, it's very easy to remove those electrons because that will make them have the same configuration as a noble gas. So we have this zigzag trend like we did with the atomic radius, but now the zigzag is upside down. I'm going to erase my marks here, but you end up with this pattern. So if we look at a periodic table where each height of the atom in this periodic table represents the ionization energy, the tall blocks represent high energies, which means it's very hard to remove the electrons, so we see that these have the highest ionization energies, whereas down here we have the lowest ionization energies. So it's exactly the opposite trend that you saw with the atomic radius, where the diagonal went in that direction. And this is because in terms of ionization energies, they get harder as you go to the right, they get harder as you get smaller. And when you add this arrow to this arrow, you end up getting this trend overall. And I'm going to erase these because these are covered in another slide, but let's just review. We haven't really talked about valence electrons. Those are defined as the S and P orbital electrons. So they can number between 1 and 8 in the atoms, and technically they can go down to 0 if they lose the entire row. They increase from left to right, and we'll talk more about these in the next unit. I don't want to spend too much time on that right now. But the atomic radius and the ionization energy, these are trends you need to know for this unit. So the atomic radius, it's essentially the size of the atom, defined as the distance between the nucleus, the center, and the outermost electrons, the edge of the atom, if you will. And as you go down, it gets much bigger, it increases, but as you go to the right, it decreases. And we learn that it gets smaller as you go to the right because of the effective nuclear charge as you add more and more protons going from left to right. But it gets much bigger as you go down because you're adding enormous new volumes of space with each time you go to a new s orbital for that atom. Now, if you look at ionization energy, that's the energy to remove the outermost electron. It's harder as you go from left to right, as you go across the periodic table. So the IE increases, and that is due to the fact that you have effective nuclear charge pulling them in, and everything wants to gain enough electrons to be like the noble gases, and you can do that by going to the right, or you can do that by going to the left. But if you're already at the right, the last thing they want to do is lose electrons. So the right side of the periodic table has very, very high IEs, whereas the left side has low IEs. As you go down the periodic table, you're getting bigger and bigger atoms, so the outermost electron is further away and it's easier to remove. Plus, you have the shielding of all the other electrons that are between it and the nucleus. So, looking in terms of the periodic table, we have these two trends. The atomic radius gets bigger to the left and to the bottom, and that gives you this diagonal pointing down to the left, whereas the IE, or IP, increases to the right and increases as you go up the periodic table, giving you the exact opposite diagonal. Notice the diagonal is the same diagonal on the periodic table, from the bottom left to the top right. They just point in opposite directions. Now, using that information, let's try to solve which is larger in this first set of questions here, oxygen or sulfur. And while the line in this particular drawing on the periodic table is blocked, blocks the actual elements, oxygen and sulfur, you can see the sulfur in green, and the oxygen is sitting right on top of it. So the oxygen's in row 2, and the sulfur is in row 3. And what that tells you is, if sulfur has another whole row added to it, well, it's going to be considerably larger. Whoops. Now we're comparing silicon versus chlorine, and I inadvertently given you the answer, but silicon is right underneath the word increases, whereas chlorine is in the yellow. It's one of the halogens, and that's the group 17s, the second from the right. And so silicon and chlorine are in the same period, but silicon is to the left, and therefore silicon has less effective nuclear charge, and therefore will be larger. Potassium, that's K, versus krypton. Potassium is on the far left of the periodic table. It's an alkali metal in red. And krypton is a noble gas all the way to the right in purple. So they're in the same row, but they're on completely opposite sides. And the left side has very low ENC, and the right side has very high ENC. So the potassium gets to be larger. It's not being pulled in by all those protons. Fluorine versus arsenic. AS is arsenic. Fluorine is in the upper right corner in yellow. It's the first halogen. And arsenic is diagonal down a couple rows to the left and a couple columns to the left. And you can see that there are two things going on here. It's to the left, so there's less less effective nuclear charge, so that makes it bigger. And you go down, it's adding much bigger size because you're adding much larger orbitals. So for two reasons, the arsenic will be bigger. Calcium versus aluminum. Calcium is an alkaline earth in orange. It's the third one down. And aluminum, you can't really see it. It is one row higher. It's right below boron. If you look on the right side, you see B. Right below that, under the word increase, is aluminum. So aluminum is one row higher. In other words, it's smaller because of that. And it's far to the right of calcium. So that makes aluminum smaller on two accounts. So calcium is the larger atom. Magnesium versus beryllium. These are both alkaline earths. They're in orange. You can see beryllium right below it is magnesium. So magnesium has a whole nother level of orbitals being added to it, so it is much larger than beryllium. Let's switch over to ionization energy or ionization potential and compare hydrogen to sodium. Sodium is Na. They're both in the far left column, the group 1 elements or 1A elements. We don't call hydrogen an alkali metal. We do call all the others in that column alkali metals, but they're both in the same group. So the question is, which one is harder to remove that electron? Which one is higher IP? And hydrogen, having an electron much closer to its nucleus, will be much harder to remove than the outermost electron of sodium. So hydrogen has a higher IP. Fluorine versus iodine. And you can't really see the fluorine. It is the topmost halogen in yellow, and iodine is several atoms down in the same group. It's also a halogen. So we're comparing two halogens. If you look in the column of halogens, it's FCl for chlorine, Br for bromine, and then iodine, and finally astatine. So fluorine is much smaller. The electrons are the outermost electron is much closer and much harder to remove than the outermost of iodine. Magnesium versus aluminum. You can see aluminum this time, and you can see magnesium. Magnesium is in orange. It's an alkaline earth metal. And aluminum is right underneath boron over on the right. It's one of the post-transition metals. So you can see that they're in the same row. So the row is not going to help you. You have to remember that the atoms to the left are going to have lower IP than the atoms on the right. The ones on the left, it's easier to remove that electron. The ones on the right, it gets harder and harder. And so aluminum has the higher IP because it has higher effective nuclear charge. Just to remind you, the effective nuclear charge makes atoms smaller, but it also makes the IP larger. So try not to get confused about that. Scandium, which is the very first transition metal in gray. If you look at that block, the D block, it is the first one. It's in row 4, the period 4, and it's the first D block atom. Scandium, named after Scandinavia, by the way, is compared with zinc. And you can't see zinc, but zinc is the last atom in that same D block row. So if I was to move the arrow out of the way, it would be right underneath the letter I in the word increases on the periodic table. That's where zinc is. So you have one on the left, one on the right, and the ones on the left are easier to remove than the electrons on the right. So zinc will have the higher IP. Oxygen versus magnesium. Well, now you have a couple effects. Oxygen is in a period 2, whereas magnesium is in period 3. So you already know that magnesium electron is much further away, and magnesium is to the left. So it has less effective nuclear charge pulling it in. So magnesium, for two reasons, is much easier to remove an electron than it is from oxygen, so oxygen has the higher IP. And the last one is strontium versus tellurium. Strontium is another alkaline earth metal in orange, 4 down. If you look, it's in the 5th row. And tellurium is underneath oxygen, which you can't really see, so it's oxygen, sulfur, selenium in green, and then below that in light blue is tellurium. It's one of the semi-metals, or metalloids. Tellurium, so they are in the same row, strontium and tellurium, but on opposite sides of the periodic table. The ones on the left are easier to remove an electron than the ones on the right, therefore tellurium will have the higher IP. And with that, that is the end of the unit, and thank you very much.